Hello, this is Professor Kuehn, and welcome back to my lectures on electricity, magnetism, and light. You might remember in my previous lecture, we finished up our discussion of Isaac Newton, his book Optics, where he argues for the particle theory of light. Unfortunately, we had to skip over chapter 19, which is called Passive Laws and Active Principles. This would have been the last chapter that we studied of Newton, but we had to skip over it. I really regret that because there's some fascinating stuff in this chapter. I'd highly recommend you read it if you have the time. He develops in this chapter some of his ideas about relating to natural theology. That is, what can one say about the existence and the properties of God given an understanding of nature that we have? So he's delving into this area where science and theology overlap, and he has some very fascinating things to say. In any case, I hope to maybe come back at some point and fill in and do a lecture on that in coming years. In any case, let's move on to the work of Thomas Young. So this is chapter 20 in A Student's Guide to the Great Physics Texts, volume 3. This chapter is titled Measuring Light's Wavelength, and this is from a course of lectures that Thomas Young prepared in about early 1800s, 1809, 1810, around there. So what I'm going to do is I'm just going to read the introductory biographical notes about Young, and then we'll jump right into his lectures. So Thomas Young, who was born in 1773, by the way, was a physician and a scientist. He was born to a Quaker family in the village of Milverton in England. By the age of 13, he was knowledgeable in Greek and Latin, Hebrew, French, and Italian. Later, he would study Near Eastern languages such as Arabic, Persian, and Chaldee, and Syriac, and Sumerian. Young continued his study of languages even while he was practicing medicine. I think this is one of the fascinating things about some of these older scientists. Many of them started out not studying mathematics and science right away. They started out by studying languages, and the kind of discipline that requires was good preparation for their scientific work. His work on Egyptian hieroglyphics played a significant role in the deciphering of the Demotic script, one of the types of characters used, the Demotic script of the Rosetta Stone, which had gone on display in London in 1802 after its recent rediscovery by Napoleon's forces during his campaign in Egypt in 1799. So you might remember that Napoleon's forces invaded Egypt. They said that they were liberating Egypt, of course. So they invaded Egypt, and while they were in Egypt, they discovered the Rosetta Stone. And a little bit of history here, they put it on one of their French boats and were taking it back to France. Some naval forces from England captured that boat, took the Rosetta Stone, and brought it to England where it was on display. And then Thomas Young, because of his expertise in languages, was one of the people that helped in deciphering the Rosetta Stone. So I'll continue reading now. During his teenage years, Thomas Young had studied Euclid's Elements and Newton's Optics. He subsequently published a number of works on the theory of light, sound, and colors, and the physiology of vision. He's also credited with coining the term energy to describe the ability of a system to accomplish work. So you might recall that we studied the work by Hermann von Helmholtz on the conservation of force. That was published in around 1850 or so, 1853, I believe. And in that lecture, we talked about the concept of energy. And the word energy, as is mentioned here, was coined by Thomas Young as the work inside of something, energy, work inside. Young was elected a Fellow of the Royal Society in 1794, which is an honor to a scientist. In 1802, he began delivering lectures at the Royal Institution, which covered a wide range of topics including pure mathematics, motion and friction, architecture, engraving, carpentry, hydraulics, hydrodynamics, sound, heat, weather, and the nature of light. So a very comprehensive set of lectures. And we have a copy of these in the Wisconsin Lutheran College library. And what we're talking about here are from those course of lectures. So in 1807, he published his comprehensive course of lectures on natural philosophy and the mechanical arts in 2 volumes. The following 2 reading selections are taken from a lecture on this course entitled On the Nature of Light and Colors. And in this book, or in this section, he carefully considers which of the 2 prevalent theories of light, the particle theory of Newton or the wave theory of Huygens, might better explain the experimental observations which had been performed by himself and by other scientists. Okay, so if you look, let's jump right away into his course of lectures. So he mentions in this first paragraph on page 234, he says, the nature of light is a subject of no material importance to the concerns of life or to the practice of the arts, but it is in many other respects extremely interesting. So understanding light, he says, you don't really need to know about this for the purposes of economy, but it's a very fascinating subject to study. I think since the time of Young, it's been found to be extremely versatile and useful area of study in addition to being interesting. And then he mentions here that the examination of the production of colors in a variety of circumstances is intimately connected with the theory of their essential properties and their causes. And we shall find that many of these phenomena will afford us considerable assistance in forming our opinion respecting the nature and the origin of light in general. So in order to he's really going to be trying to understand not just how light behaves, but why it behaves the way it does. In particular, is the wave theory of light or the particle theory of light better able to account for the observed properties of light? And now what he's going to do is he's going to mention in the second paragraph here on page 234 that he's going to summarize what the viewpoints of Newton and Huygens are. So he says, it is allowed on all sides, or everybody agrees, that light either consists in the emission of very minute particles from luminous substances, which are actually projected and continue to move with the velocity commonly attributed to light, or, on the other hand, in the excitation of an undulatory motion analogous to that which constitutes sound in a highly light and elastic medium pervading the universe. So those are the two options. It's an emanation theory of light, particle theory of light, or the undulatory wave theory of light. He says that, he goes on to say, the judgments of philosophers of all ages have been divided with respect to the preference of one or the other of these opinions. There are also some circumstances which induce those who entertain the first hypothesis, the particle theory, either to believe with Newton that the emanation of particles is always attended by the undulation of an ethereal medium, accompanying it in its passage, or to suppose with Boscovich, Father Boscovich, another philosopher and scientist, that the minute particles of light themselves receive at the time of their emission certain rotary and vibratory motions. So what's he saying here? He's saying even those who believe in the particle theory of light, there are some kind of variations on this particle theory of light. Some who believe in the particle theory of light believe that there is also an ether that interacts with these particles and kind of causes them to swerve or diverge or to bend. And then there are other people like Father Boscovich who said, well, I believe in the particle theory of light, but when these particles are emanated, they also spin or vibrate in some way. But he goes on to say that these are kind of unusual beliefs, and the basic beliefs are the particle theory and the wave theory. Okay, and then he says in the last paragraph on page 234, he says, we shall proceed to examine in detail the manner in which the two principal hypotheses respecting light may be applied to its various properties and affections, and in the first place to the simple propagation of light in straight lines through a vacuum. So he's going to go through a number of experiments and say whether or not the particle theory or the wave theory is better to account for the observed properties of light. So he starts out on this last paragraph here talking about the fact that light goes in a straight line. And which one is better able to explain the straight line propagation of light? Well, he goes on to say that they both work really well. So if you think of light as being a particle, just by the principle of inertia, an object in motion tends to stay in motion in a straight line unless a force acts on it. If you believe in that principle of inertia, and you believe that light is a particle, it only makes sense that light would travel in a straight line, because these particles would just keep going in a straight line once they're fired out by a candle or whatever produces them. The Huygens or wave theory of light, he says, also can account for the straight line propagation of light. So you might remember how Huygens directly addressed this issue and said that when light travels through an aperture, it will travel in a straight line, but there will be a little bit of spreading, but this spreading will be small. And moreover, and this is something that Young points out on the next page, where this could be seen as a problem, Huygens is able to explain that it travels in a straight line with a little bit of spreading, and the amount of spreading depends on the wavelength of the light. So he mentions that if you have water waves traveling through an aperture, there's quite a lot of spreading beyond the aperture. But if you have waves of shorter wavelength, the spreading is less and less as the wavelength gets smaller and smaller compared to the aperture size. And so by deduction, one would conclude that if you have a wave that the wavelength is very, very small, like light, for example, then it would experience very little spreading or divergence, and it would travel more and more in a straight line. So this is how the wave theory and the particle theory, as Young points out here, are both conformable to the observed behavior of light. Okay, now what about the next topic he brings up? This is on page 235, the bottom, at the last paragraph, he says, with respect, however, to the transmission of light through perfectly transparent mediums of considerable density, the system of emanation, the particle theory, labors under some difficulties. So he says that if you believe in the particle theory of light, you're going to have a little bit more trouble explaining the transparency of materials like glass. Why would that be? Well, if you go on to the next page and read this sort of long paragraph at the top, what he's getting at is if glass is comprised of physical particles, it seems strange that particles of light would be able to fly through it without bouncing back, right? So if you think about, I'm going to draw a picture here. If you think about a block of glass like this, even if it's a very thin block of glass, presumably it's comprised of atoms or particles, right? So you've got all these little particles that comprise or make up the glass. And if you believe this, as Newton presumably did, then it would be very strange to have a bunch of particles of light flying toward it and be able to make it all the way through, in the case of glass, without having bounced off or been reflected by any of these particles. And what he does here is he tries to do some calculations to estimate how rare or how wide of spacing there must be between these atoms or molecules of glass so as to allow the kind of transmission that we see through glass. And he uses this analogy. He says it would be almost like if all of England was filled with only 100 men. That's how widely spaced these molecules of glass would be in a block of glass, which is very, very rare. And he says that sounds implausible given the fact that glass is a hard substance. So that's one that he presents that. Now, you might not see this as a slam dunk, but he's saying this sounds implausible. You need to have very rare composition of this in order to allow light particles to fly through. And then he goes on to say that if you think of light instead as a wave, it doesn't labor under these same difficulties. He says the reason for that is because if light waves come in and strike the glass, what happens? Why would it be transmitted? Well, if the molecules of glass themselves are able to vibrate and partake in this motion, then there's no reason why those waves would not go through. Okay, so he says that the wave theory seems to provide a better explanation of the transparency of glass than the particle theory would. And again, you may or may not find this convincing. I think you need to weigh these sorts of arguments when considering the work of Young. The last paragraph on page 236, he presents what I think is one of his stronger arguments for the wave theory of light. And spoiler alert, Young is a proponent of the wave theory of light. That's part of what he's doing here, is he's comparing and contrasting them. He's going to come out and say the wave theory is the better theory. The topic he's talking about on the bottom of page 236 is the uniform velocity of light in the same medium. That is, if you have some medium like glass or like air or like what seems to be the ether, the vacuum of space full of ether, it seems strange that light from all different sources would travel at the exact same speed if light was a particle. Okay, so why is that a problem? Well, he brings up the topic of, let's suppose that you burn a piece of wood, or you burn a piece of iron, or you have a star burning. In all of those cases, light is produced. And if you believe the particle theory of light that Newton is advocating, these particles of light must be shot out of this burning substance. And it would seem really, really strange for the particles of light shot out from a burning piece of wood to fly with the exact same speed as the particles being shot out by something like the sun, which is much, much hotter than the wood. But since light from all these different sources travels at the same speed, it seems to militate against this particle theory of light. It's very weird that all these sources would be able to throw light particles with the exact same speed, as far as we can measure it. So he says some very interesting things at the bottom of page 236. He talks about the calculations of Mr. Laplace. Laplace was a French mathematician and scientist. And what Laplace calculated was, if we take this particle theory of light of Newton's seriously, that is, particles should be emitted from some burning object. If these particles are shot out from, let's say, a candle, and they're shot upward, let's say, away from the Earth, then because of Earth's gravity, they should be pulled back down towards the Earth. And there should be some speed below which those particles will not be able to escape the gravitational field of the Earth, and those light particles would fall back toward the Earth. So if this sounds familiar or very modern, then you're thinking about this correctly. He's basically suggesting that there could be such thing as a black hole, right? This is, remember, 1800. Laplace calculated that if you have some particle of light that's shot upward with some velocity, because of the Earth's gravitational field, if this is in fact a particle with some mass, the particle will head upward, but if it has too small of a velocity, then it will eventually, instead of escaping, it will fall back down to Earth. And so you will have, if you're standing out here somewhere looking down at the Earth, none of the light would be emitted by the candle. Okay? And that was a calculation that Laplace had done. And that's something that Young is mentioning right here. He says, Mr. Laplace has calculated that if any of the stars were 250 times as great in diameter as the Sun, its attraction would be so strong as to destroy the whole momentum of the corpuscles of light proceeding from it, and to render the star invisible at a great distance. So if you had the star that was so massive that the gravitational force was great, the light being emitted from it would not be able to escape it and would fall back, and you'd actually have a black hole. He doesn't use that term here. He says, and although there is no reason to imagine that any of the stars are actually of this magnitude, yet some of them are probably many times greater than that of our Sun, and therefore large enough to produce such a retardation in the motion of their light as would materially alter its effects. So he says here that it's presumably true that some stars would be big enough to be able for the gravitational force to prevent their light from escaping, and so these things would be there in nature. And yet we do see very large stars and we can see the light from them. Therefore, the particle theory of light is not such a good theory of light. That's the reasoning behind this. And then he goes on at the bottom of the first paragraph on page 237 to say the wave theory of light is can very easily account for the uniformity of the speed of light. Why is that? Well, because no matter what the source of light, whether a burning piece of wood or a burning piece of iron or a burning star, it doesn't matter what the source is, because for waves, the speed of a wave is governed not by the source, but by the medium itself. So the stiffness of the medium is what governs the speed of a wave. So as an example, think about sound waves. It doesn't matter whether I shout or I whisper, the speed of sound of those two noises will travel at the same speed. Why is it? Because the speed is not governed by my throat and my mouth, it's governed by the density of the air and the properties of the air. And that's the case whenever you have waves traveling through a medium. The medium itself governs the speed of the wave, and so it's not surprising that if light is a wave in a medium, then different sources would have light that's all traveling at the same speed. So once again, the wave theory is better able to account for the uniformity of the speed of light from different sources. Okay, tell you what, I'm going to stop there, and I'll continue this lecture next time.